All right, hello everyone. Today is Monday. This is our class number 9, I believe, which we're going to do the regularization, Lasso and ElasticNet in Python. So for today, I have 2 exercises for you. The first one is a simulated data, because the example that we are as if we are the God and we know what is the true relationship between variables. And then, so that's why we are going to work with simulated data. And we want to figure out which of these models are going to do a better job, Ridge versus Lasso versus Elastic. And then before we get super excited, we want to work with the real world example and see what are the challenges that we work with Ridge and Lasso and ElasticNet, right? So I have another example when we are going to work with the Boston data set. We only pick 2 variables, I think the price, the median price, and LStat, a lower status. And we know that they're negatively related. The relationship was nonlinear, but we want to see which of these models are going to do a better job, or can they outbid our simple linear regression model or not. So that's the plan. All right. So if you update your GitHub repository, you should see this folder, class 9 and regularization Python. And I put the HTML version as well. For those of you, I don't know, who wants to read these things on the go, you don't have Python necessarily installed on your iPad or things like that. You can always open up the HTML and review things faster. You don't need to open up Jupyter Notebook. Okay, so let me close this one. So first, we're going to start with synthetic data. I'm going to have this contextual help open here. Because maybe it's a good idea to look at the documentation of some of these functions as well. All right, so this is our true model, right? So the true relationship between y and x, we know that the true relationship is x plus 2x squared minus 3x cubed plus some noise, right? We know that this is a true relationship between x and y out there. However, we're gonna, let's say we don't know, and we're gonna throw x squared, x to the power of 3 to the power of 4 and to the power of 5, and then run ridge regression, elastic, and lasso, and see which one is being able to put, let's say, lower weights on the coefficient for x1 and x5, or completely get rid of those ones, right? Depending on what's the penalty term or shrinkage term. Okay. All right. As always, we start by importing the libraries. So these are standard NumPy, Pandas, Matplotlib, Seaborn, scikit-learn, linear regression, and stats model API. So this is not part of the machine learning part. I only added there because I wanted to give you a benchmark when you want to compare the models with our simple linear regression model, but at the same time, I wanted to see the p-values and t-statistics and see which one is more significant or not versus the other, right? But usually for practical purposes, usually the chances that you work with stats model API is very small. Anyways, and I'm going to go ahead and ignore the warnings, because the reason that for this exercise, usually I don't ignore the warnings because they're constructive. They tell you something, for example, what are the updates in the next version of the formula, things like that. But for this one, you will get lots of those warnings. The reason is that the lasso and ElasticNets, we know that they are we have to do gradient descent. Sometimes the algorithm does not necessarily converge, and sometimes you get large warnings. So for that reason, I actually try to ignore the warnings for now. But there's an exercise down the road on this notebook that I want you to just comment this out and see what are the warnings and if you can figure out what's going on. So stay with me for that question. All right. So random state, again, if you want to see the exact numbers that as I have here, because when you're splitting the data, you're doing that based on some random state. When you're doing cross-validation, you're doing based on some random state. So this is just for convenience. You can do 1000 to see exactly the same numbers. We are going to work with this regularization synthetic data. And if you look at the head of the data set, so this is our x1. And basically, this is our main feature, and we're going to x to the power of 2, to the power of 3, 4, 5, and this is our target variable, right? Let's look at the true relationship between y and x. So again, x1 is our x. And it seems that, well, it is nonlinear, and we're going to see which of our linear regression models are going to able to capture this nonlinearity better. So that's the plan, okay? However, so again, guys, remember, whenever you're working with penalized regressions, always before doing anything, you have to standardize the variables, right? This is important. Why? We talked about this one. Why? Why standardization is a big deal in penalized regression? Any idea? Thoughts? Yep. Yeah, because remember, think of the loss function in penalized regression. We have L1 norm or L2 norm or a combination of the two, which is, if it is L2 norm, it's scoring the betas to the power of 2 and then adding them together, right? So if one beta is in 1,000, the other beta is in percentage, it doesn't make sense to compare them or shrink them, right? So we have to make sure that we standardize all the variables first. Then it means that the features, the coefficients are also comparable. We can compare beta 1 to beta 2, beta 3, and in machine learning language, W's, the weights. Okay, so that's the answer to this question. Okay, now how do we do that in Python? So you have to use one of the classes from scikit-learn class. It's called pre-processing, and you're going to import a standard scalar. So this is a function or class of functions. And then now the standard scale is imported. Now here you have to define an object, and I call it a scalar. You can call it anything, but this one of this should be an object, right? We say that object is we're saving this function, a standard scalar function in that object, right? And then when this function is saved, you can do fit transform. You can do fit transform to any data frame that you have. Remember, this is our data frame. Now, if I do fit transform standard scalar, what it does behind the scene is going to take any of these values, subtract the average, divided by standard deviation. So this is our normal process of a standardization, right? So, and we can do it by running this line. Again, I define this object, standard scalar, and then I do fit transform. I pass my data frame, and I make a new data frame. I call it df_SC, stands for scaled. And I can look at that. Actually, let's look at the entire data frame. So this is the entire data frame, right? So it has, so for example, do you see these brackets? So it has, so the first row is basically these 1, 2, 3, 4, 5, 6, these 6 observations, right? If I look at the first row, so basically this 1.68 is a standardized version of this 1.66, right? I think for Y, it makes more sense because X's were drawn from a normal distribution. So if you do standard normalization, it doesn't make that big of a difference. But for Y, it was quite sensible. Look at the magnitude of Y. Y goes from, let's say, plus 60 to minus 100 here. But if you do standardization, it should be between -3 plus 3 with 99% probability, right? So let's look at this number, for example. Take this number, we want to standardize it. -3.9, right? And something. So let's check it out. I'm going to say -3.9 minus the average of Y. What is the average of Y? 3.16 divided by standard deviation of Y. Standard deviation of Y, 17.25. Again, I do this step only to visually check that if the standardization is being properly done, or I didn't make any mistake, right? So this number should be around -0.4. And if I go back to the first, no, actually, if I look at the data frame that I construct out of this scaled data set, Y is -4.1. Well, of course, there's some rounding errors, and that makes sense, right? So the standardization is being done properly. If I plot the Y versus X again, and I want you to compare this plot, and this one. You see the pattern, everything is the same, right? When you're doing standardization, you're not touching the pattern, right? It's not like log transformation. Log transformation is changing the pattern, but standardization doesn't change the pattern. But the scale is different, right? Here, the scale of X, because X was drawn from a normal standard distribution, it doesn't make any changes to that. But for Y, it used to be between 60 and -100. Now it's between 3 and -3. Again, this is obviously an outlier. What does this mean? 6 standard deviation above or below the average in this case, which is absolutely an outlier, right? Okay, so now our data set is ready, right? So I have a new data set. We call it df_SC scaled. And now let's play around with this data set. So our first job is to split the data. We are going to call Y and X based on, so the target variable is Y in the data set, the name was Y, and X are the features. We're going to say, take that data frame drop the target variable and give me back everything else, right? What are everything else? X1 through X5, right? So and then this is we talked about it. This is a faster way to do that. You could have done it like this, bracket X1, X2, X3 up to X5, and then close bracket. But if you're doing it this way, please make sure that the in place is false, because you don't want to replace the DF under this data set with the original one. Okay, now we're going to set the test set size 20% on random state, which is our 1000. So this means that the train set is 80%, right? Okay, let's look at, so we can just, to double check, we can look at the X train, of the head of the X train. Of course, these numbers are randomly selected. If your random state is different, these numbers are going to be different. So for example, if I do, I don't know, some number, these are different splits from the data, right? So let's all right. And so as you can see from this table, the variables are highly correlated, right? Not surprisingly, if you do the VIF test, variance inflation factor in our linear regression model on this, on these variables, they're easily going to be all of them greater than 50, I guess, or 60, right? Because they're highly correlated, x squared, x to the power of 3, and etc. When you look at the numbers, so 6, 6, 8, 7, 6, 7, 5. Again, if you look at if you calculate the correlation, it's going to be highly correlated. So this means that there's a good chance if I use my simple linear regression model. When I say simple, I don't mean one variable. I mean linear regression, because if you use our linear regression model, there is going to be a chance that they're highly correlated and we get fake significancy, right? So for example, those are the problems of multilinearity, right? But in machine learning, we're not worried about them, right? So we will see if, for example, ridge regression, Lasso and ElasticNet are able to reduce that collinearity and give us back the most important features, right? So that's the plan. So this part, these 4 lines, again, in machine learning, we usually don't use that, but I just want to see you the coefficient for yourself to have some, again, have some benchmark at the back of your head. But this is not something that you should, or you want to do necessarily in machine learning. So because I'm going to only use it once in this for this notebook, I'm going to give the tested and trained set new name. So I'm going to call it X test. WC stands for let's say with constant. I'm adding a constant, and X train with constant. The reason that we have to add a constant, and we're using this SM. Remember, this is a stats model API from the top. The reason that we need to add constant to the model is that by construction, the author of the package didn't have the constant, so you have to add it manually. But when you do linear regression from scikit-learn package, automatically that constant is there. You don't need to add it manually. Okay. Looking at the coefficients cannot be easier than this. So we say, okay, from that package, I want to do OLS. Train the model using the train set. As you can see, Y train and X train WC. Again, Y doesn't make sense to add a constant to the target variable, right? And then finally, you fit it. And as you can see, we're fitting it in the train set as well. So let's look at the coefficient in the train set and just get a sense that which of them are most significant, right? So first of all, the R square is 45%, or adjusted R square 40%. In this case, is more relevant to look at the adjusted R square in the train set because we have high collinearity. So it's 40%, it's not that bad, but look at the coefficients. So if I look at coefficients, and guys, remember, I know ex ante, this is the answer, right? I know that. No, I know the true relationship between variable. And the magnitudes are going to be different because we standardize this Y, but the signs should be something like this. So for example, we have positive, positive, negative, and this negative to the power of 3 is greater than this positive and this positive, right? And then there is no sign of x to the power of 4 or x to the power of 5. Let's see, what did our simple regression model do? So let's look at the coefficient. X1, if you look at the p-value, so it's good, it's significant at 0.008 and above. So this is significant at 1%. X2 is not significant, right? So our linear regression model says that maybe X2 should be dropped. It's not significant. X3 is significant, and we know that it's an important feature in our true model. However, X4 and X5 are also significant. So this is not good, right? So this is a sign that our linear regression model, oh, sorry, they're not significant, sorry. So they're not significant. And again, maybe this is a sign that these should be dropped from the model, right? When we do linear regression model, right? Now let's, so with that in mind, let's go ahead and run the machine learning version of the regression analysis and the penalized version, ridge regression, lasso, and ElasticNet regression. So is the setup clear what you're doing? Okay. So we are going to import from linear model, scikit-learn package, import the linear regression, ridge cross-validation, lasso cross-validation, ElasticNet, and ElasticNet cross-validation. Okay. And and of course, obviously, we are going to use ridge cross-validation for ridge and etc. So let's first define our objects, define our models. So I'm going to do them all in one cell for all the 4 models. So the first cell is going to define our model. I give it, this is the name that I give it. So model linear. So this is our linear regression model, model ridge, lasso, and model net. So net is for our ElasticNet. And I'm going to, for now, I'm going to pass, for linear regression, I don't pass anything. So these are, maybe this is a time that we can look at the contextual help. For linear regression, I don't pass anything. It means that everything should, all the default properties are going to be considered, right? And linear regression would work with it. Then ridge regression, if you look at, let me run it. Oh, I haven't run this line. That's why it doesn't pull up. Yep. For ridge regression, as you can see, alpha, this is our shrinkage term, or so, well, in ridge, we call it shrinkage. In maybe lasso, we can call it feature selection term. And so I'm going to say, I'm going to start with alpha is equal to 0 for all of them, for ridge, lasso, and ElasticNet. But in our next exercise, we're going to see that this is not necessarily the best way to start with, because again, we're going to talk about it in especially in lasso and ElasticNet, because they are not stable. Sometimes the path to the coefficients are jumpy, they go up and down. So for that reason, starting from 0 is not necessarily good. But in this example, because the data is simulated, I know that we can get exact same numbers. So what do you think if I put alpha is equal to 0 for all the 3 models? What should I get? The same thing as the linear regression model, right? So if alpha is equal to 0, if you go back to the slides, we should get exactly the same thing. So remember, alpha in Python is our lambdas, right? If lambdas are 0, so I get the same MSE for ElasticNet, the same story for lasso. Again, lambda is equal to 0, and the same story for our ridge regression, right? So not surprisingly, we should get exactly the same answers as the linear regression, but let's move. And so for ridge, these are the, by default, the alpha is 1, but I just wanted, for fun, I want to start from 0. For lasso, again, default is 1. For ElasticNet, there are a couple of things that you should consider. So there's one thing, so the way that we did it in on the slides is we have lambda 1 and lambda 2, right? Lambda 1 was a coefficient for the L1, lambda 2 was a coefficient for L2, right? However, in Python, the notation is kind of different. So here's the notation for Python. So this is the function that Python is minimizing, right? It had, this is our, so y minus y hat, again, it really doesn't matter. We're scoring it, so it really doesn't matter if you call it y hat minus y or y minus y hat. And as you can see, the notation is slightly different. And this subscript 2 stands for L2. So we are making something to the power of 2. This is L2 norm. Okay. This is our L1 norm, and this is our L2 norm, right? But I don't have lambda 1, lambda 2. This is what we have. Alpha multiply P and alpha multiply 1 minus P, alpha divided by 2 multiply 1 minus P. So what we're doing here is it's not that complicated. We call this rho L1 ratio. So basically, that's how you want to emphasize on the L1 part of the penalty function versus L2, right? If rho is equal to 1, what do we get? Everything is going to be L1. Does everyone see that? If rho is equal to 0, then everything is going to be L2. So that's why we call L1 rho as L1 ratio, right? By default in Python, this ratio is 50%. So it wants you to, by default, think of 50% L1, 50% L2, and then go ahead and look for alpha. Alpha, the interpretation of alpha is exactly the same. If alpha is 0, we get the linear regression. If alpha is higher, you're penalizing the regression more strictly. Does that make sense? Yep.
Why, maybe I'm just forgetting the equation, but why is the weight for 2, L2 divided by 2?
This one?
No, the end term. Yeah,
This
like
one?
that.
Well, again, the notation is that because if you want to get something, so if you read the documentation for Python, and it says that if you want to think of L1 and L2 penalties separately, so something like this, you can think of this A and B, and alpha is defined as A plus B, and L1 ratio is defined as A divided by A plus B. The reason that we have that too, because you can separate these L1 and L2 parts. Mathematically, it works better. That's all, right? But otherwise, in terms of optimization, it doesn't do anything, right? It just wants to make sure that those add up to, for example, 1, or you can play around with the fraction of L1 versus L2. Yeah, good question. Okay, so for this exercise, actually, for all the notebooks that we do, and also for the homeworks, I want you to just stick with this L1 ratio of 0.5, so you don't need to pass it to the ElasticNet. And the reason is that you want to see 50-50 combination of the, let's say, L1 and L2, right? But again, you can play around with it and see which one is the best combination. All right. So these are the models. So our first step, guys, remember, we're gonna actually, I'm gonna do the first and second step together. I'm gonna fit the model, use train set, and make prediction using test set, right? So this is pretty straightforward. And you're gonna save the outputs in the y hat underscore whatever the model is. So y hat linear, y hat ridge regression, y hat lasso, and y hat net, right? And for visualization purposes, I make a data frame out of these things and give them proper names. So let's look at that data frame. I call it DF prediction. So these are the prediction, not surprisingly. So again, this is my true actual y in the test set, 1.3. And these are the predictions by linear model, ridge regression, lasso, and ElasticNet. We are not surprised that they are exactly the same numbers, right? Because alpha, we started from alpha is equal to 0. Okay. Now let's look at the coefficients. And again, I'm going to make a new data frame. I call it coefficients. And this is the way that I just define the columns in that data frame, right? So I'm adding the new column. What is that new column? What is inside that new column? From model linear, the coefficient of that model, right? From ridge regression, the coefficient. From lasso, the coefficient. And from ElasticNet, the coefficient, right? Again, I think we talked about it earlier. I'm not going to go over the details of every single line. So I assume that you review the Python the basics and etc. And hopefully you can, if you have any questions, just let me or the TAs know. These are the coefficients. Again, not surprisingly, the coefficients are all exactly the same as our linear model. These are the coefficients that we saw up there from stats model 2 as well. And then we know that, for example, only x1 is significant. x1 and x3 are significant. The rest of them are insignificant. Now let's let the machine do the job and see if we can optimize over it or not, right? In terms of performance metrics, this is regression. We look at RMSE, and we of course look at the RMSE in the test set. So let's look at the RMSE in the test set. For the first one is going to be my linear model, y minus y hat linear. So RMSE is 2.037. And not surprisingly, for the ridge regression, same number for lasso, same for ElasticNet, same, right? Because they're all, the alpha is equal to 0, right? Okay, now let's plot the regression coefficients versus alpha. Now we're going to start playing around with that alpha. We're going to increase the alpha and see what's the effect of that alpha on the coefficients. I know that in ridge regression, if I increase the alpha, the coefficients will move towards 0, but never 0. But in lasso and ElasticNet, as I'm increasing the alpha, the coefficients, some of them will be completely equal to 0, right? Okay, so I'm going to define a range for alpha. I call it, so this is the range for my alpha ridge, right? So we're going to start with for the plots by plotting the ridge regression versus alpha, the coefficients versus alpha. But before that, I want to define a range for the alphas that I want to pass to the model, right? So this range, so I'm going to say that it's 100 numbers starting from 10 to the power of minus 2 to 10 to the power of 4. As you can see, 10 to the power of minus 2 is almost 0, 1%. and then 10 to the power of 4, it's 10,000. The reason that we're doing it this way is that, guys, remember, at the end of the day, I want to pass these alphas to my ridge regression model and then plot the coefficient path for different alphas, right? The reason that it is convenient, and it is convenient to do it this way, because you want to make sure that you start from these, each incremental is, you want to make sure that when alpha is small, you're adding to the alphas very little by little, right? But eventually, gradually, you want to increase the alphas so dramatically that at the end of the day, you want to make sure that the coefficients are converging towards 0 in your ridge regression, or in elastic or lasso, they're exactly equal to 0. Does that make sense why we do it this way? You could have, for example, you say, okay, I want to do a range between -2, let's say, and 4. Well, -2 and 4 doesn't make sense. Let's say between 0,001 and 10,000. You can still pass some alpha like this to the model, but you're going to see that I'm going to try this again, but and you'll see that the path is not necessarily smooth, right? Because you want to make sure that when alpha is small, you have enough of those small alphas compared to each other. But right now, look at that. For example, the first one, the alpha, I don't know, it's 0.001. The next one is going to be a lot higher, right? Let's actually look at that. Alpha, right? No, ridge. You see, the first one is small, but the next one, right? The next one is almost 10. The next one is 20. This is too big, right? So for that reason, we don't like this kind of range for alpha. We're going to say that, okay, let's do it to the power of 10. And then this is usually, again, in practice, I think everybody do something like this, because again, it gives you more smooth path for alphas. And at the same time, make sure that you are increasing these alphas enough to make sure that the ridge regression is, the coefficients are converging. Is this clear? Okay. Now let's plot this, right? I'm gonna go ahead and define an object. I call it ridge, and I want to save the coefficient of ridge in a list. So outside the loop, I define an empty list, and this is my model. I call it ridge, and then I say for I in alpha ridge, right? So this is, I'm going to say that for all these 100 dots, do this. When alpha is equal to 0.001, do the ridge regression, save the coefficient. When alpha is equal to 10, do the regression, save the coefficient, and etc. This is what this for loop is doing, right? So inside the for loop, we say ridge set parameters. So again, for every iteration, we're changing the alpha, and alpha is equal to I. And again, fit the model. And when you fit the model, just append the coefficients, right? So this is how we define the coefficients. And you can look at the size, shape of the coefficients. Not surprisingly, it's 100 by 5, because we have 5 variables. And so basically 5 coefficients and 100 different numbers for 100 different values of alphas. And you can plot it. This is how it looks like, right? So if you plot the coefficients of ridge regression versus alpha, this is what we discussed over the slide. So again, I think I don't need to go over the details of it, but if you look at it, for example, when, I don't know, when alpha is equal to 100, so it seems that the green one is the most, it's still one of the most important ones, X3, which is good news. And then after that, we have this yellow one, well, orange one, X2. Again, it makes more sense. And after that, we have this X4. This doesn't make that much sense, right? And then maybe here we have X1 and X5. So we know that the ridge regression cannot get rid of any of these variables. So at the end of the day, what it does, it just shrinks them, doesn't force them to be 0. Okay. We're going to repeat exactly the same process. Let me close out this one. Exactly the same process for ElasticNet and Lasso. So the next one is Lasso. And here for Lasso, I'm going to start with a smaller alpha. So it's 1/1000th instead of 100th. So the reason is that I just plotted with 100 and I saw that I need more granularity. So I went back a little more. So again, the rest is exactly the same. So here is the coefficient path for Lasso, and now it starts shining right at you, right? because look at the power of lasso. So for example, we see that if alpha is equal to 1%, so x3 is there, and then x2 is there. If alpha is equal to, let's say, 0.01, so sorry, this was 10%, this is 1%. If it is 1%, so x3 is the most, well, in terms of magnitude, is the largest one, and then is x1, and then is x2. So this is very close to reality, right? Remember our true model? So this is very close to reality, and we saw, and not surprisingly, Lasso should do a lot better job than our linear model, right? So by looking at this coefficient path, we know that Lasso should do a better job. And then finally, for ElasticNet, so again, we have to first define the alpha ElasticNet, and then let's plot it. So this is, for ElasticNet, we're going to look at the optimal coefficients at the end of the day, because the numbers are very, very tiny. So these are very close to each other. So the path, it's as if exactly equal to Lasso, but it's not exactly equal. So we're going to look at the numbers on a table in a minute, and we'll figure out they're slightly different. All right. Are we good so far? Okay, now let's do cross-validation. So why do we use cross-validation? Guys, remember, the main usage of cross-validation is to tune the hyperparameters, right? So the secondary objective is to estimate, for example, the MSE of the test set. But when you do have the test set, when you want to compare the models, you simply compare the RMSE of, for example, ridge regression in the test set with the RMSE of the lasso in the test set when the test set is there, right? So the use case for cross-validation is first tuning the hyperparameters and then estimating the performance metrics in the test set. Because again, I'm emphasizing, if you do have the test set, if the test set is already labeled, that's your best case when you want to compare models, right? However, when you're doing cross-validation, when you're tuning the hyperparameters, you want to tune the hyperparameter of the model on a data set that the model is not going to see it for the test set. Does that make sense for the performance metrics in the test set? So for that reason, we do cross-validation. But at the same time, we don't want to do the, for example, hyperparameter tuning in the train set, because that's completely cheating. You know, the train set is completely observable to the data, to the model. So for that reason, we do the cross-validation. Is this clear? I think I was not clear on this usage of cross-validation previously. But some people made comments. I think Tristan, you did, right? Made a comment on the YouTube, and I realized that maybe I should talk about it more. So the first application of the use case of the cross-validation is for hyperparameter tuning, and the secondary objective is to estimate those test sets. If you the performance metrics in the test set, if you already have the test set is labeled, you trust those numbers, okay? Because that's your best benchmark to compare different models among each other. Okay? Can you repeat the second reason? The second, estimating the performance metrics in the test set. But if the test set is already labeled, you trust those performance metrics already, right? So we're going to look at it down the road in this notebook, but I just wanted to clear out. Okay, now, so the goal of doing cross-validation is to figure out what are the hyperparameters in these three models: Ridge, Lasso, and ElasticNet. So hyperparameter, the only one that we're considering is alpha, right? So let's optimize the alpha. So in polynomial regression, remember, what was the hyperparameter? It was the degree of polynomial, 1, 2, 3, 4, 5, and etc., right? Because so this is important, guys, pay attention. Because a hyperparameter in polynomial regression was discrete, it was 1, 2, 3, 4, 5. I could literally put it in a for loop and plot the RMSE of the test set and use the ALBA method and figure out where is the optimal value for a hyperparameter. Are you following? However, for alpha, this is not discrete. And as you can see, alpha can be any number, right? It can go for, in this case, I define only 100 of these alphas. But you know that, for example, if you want to go between 0 and 10,000, there are millions of those alphas, right? Because this is a continuous random variable. So for that reason, the ALBA method that you're used to work with in polynomial regression using cross-validation maybe not be the best solution, right? So this is the bad news. The bad news is that the computation is heavy. The good news is that there's a built-in function in Python. So that's why we have to import the Ridge cross-validation, Lasso cross-validation. So behind the scene, that function is doing gradient descent to optimize this continuous hyperparameter. Does that make sense? Okay, so application is easy. This is the application. Let's say this one. Literally 2 lines of code, right? So we call it RidgeCV. This is an object, and I define, again, we are importing this from scikit-learn linear models class, and then we fit in the train set, and we can, out of this object, guys, when we are passing this train set, automatically behind the scene is doing cross validation. So 5-fold, k-fold, and etc. You can change the number of folds, by the way. So if I do this contextual help, we can play around with the features of this cross, where is that? Cross validation. So by default, if you do not pass out any alpha, it's going to take these ones. And let's see, cross validation, for example, we can play around with the cross validation and etc. Right? You can pass a range, or you just let the model does its job. So it seems that if I don't pass any parameters to the model, so it's basically going over these ones and find the optimal one, right? So here the optimal one is going to give you back 1. So 1 is going to be the optimal alpha for using ridge regression, right? I'm going to save this alpha. I give it a name, alpha ridge optimized, and so I save it, right? Because we're going to use it later on. We're going to go back to the beginning of the code and use them later on. See if we can beat our linear regression model or not, right? So we're done with the finding the hyperparameter for ridge regression. It turns out to be 1 here. Again, if you want to be more precise, you can pass a complete range maybe here, or maybe, but you have to literally pass it, right? So maybe 100 numbers. And this is computationally heavy. So if you have 1 million observation, and if you want to pass 100 of these alphas, so it's going to take a while. But in our data set, which was tiny, so we can actually try that. But let's stick to the one that comes with the defaults, right? As a default. The next one is we are optimizing the alphas for Lasso. Again, so for Lasso, the story is different. So as you can see, there is no alpha defined. So for Lasso, it's going to do that gradient descent behind the scene. It's going to give you exact number. And the optimal value for alpha is going to be 0.0045. So this is the optimal value for alpha in Lasso, right? Let's go ahead and save it. We're going to reuse it again. And then finally, let's find the alpha for ElasticNet. Again, for ElasticNet, as you can see, the default L1 ratio is 50%. It means that 50% L1, 50% L2. But we want to figure out what is the best number for alpha. So the best coefficient for alpha is equal to 0.006. And I just wanted to show you that you can extract all other attributes from that class, from that object as well. So for example, if I want to see what was the L1 ratio, so L1 ratio was 0.5. I'm going to go ahead and save it. So here, you don't need to do that in practice. But I just wanted to show you that for fun, we can do our traditional elbow method and see if that works or not, right? So I'm going to say, let's say these are, we're going to, let me actually import this thing. Again, guys, for application purposes, you don't need to do this part. This is just for fun. And this is not accurate because we know that we are not exploiting all the information. This is continuous random variable. We are passing some discrete numbers to that, right? So we're going to say that calculate the RMSE cross-validated version. And again, I do it for ElasticNet only. Let's change these alphas from this iterator. So it's a range from 0 to 0.02. And we're increasing it by just 1,000th, right? And we can look at we have seen this code before in our polynomial regression. This is exactly the same code. We're just simply changing the model, and we're saying that, okay, calculate this RMSE, the cross-validated version for different alphas, right? We can look at the output. So this is our output. Now we can do the elbow method, right? So we can plot this thing. Actually, let me run these 2 lines. We can plot this thing and do the elbow method. As you can see, it seems that the minimum is going to be around here, right? I call it lambda, but this is our alpha, right? And but we can figure out where is that, what is the location of that minimum number? So by calling IDX mean, index mean. So this, it says that it's your 7th observation in the data frame. So this is the output data frame, 7th observation, and say, okay, give me the argmax of it. So, or argmean of it. So what was that number? So that number was 0.007. So it seems that if I wanted to do our traditional cross-validation that we did for discrete hyperparameter, the number that I could get was around 0.007. Does everyone see that? Right? However, if you just run this function from ElasticNetCV, the optimal number was 0.0064. So we are close, but of course I should trust this number compared to the ELBA method. I just wanted to visually show you that how ELBA method works, and you to think about it and realize that why we do not ELBA method in penalized regression, because our polynomial, not polynomial, our hyperparameter is continuous. Okay. All right, is this clear? Is there any questions? Okay, now, so let's see, let's go ahead. So we're not done yet. That's just, we figure out what are the optimal values for alpha. Now let's go back and refit the 3 models with the optimal version of the alphas, right? And see if they can outfit the linear regression. So let's go back. Now I have saved them. Let's go back to the top part when we were fitting the models. So here. So now instead of using 0, I'm going to use the optimized version. So alpha, I think alpha rich, we should have optimal. Then, oops. We have here, I'm going to use alpha lasso optimal. I'm going to use alpha ElasticNet optimal, right? Now, if I run the code, of course, the y-hats are going to change. Not for, as you can see, the y-hats are going to change. The more fun part are the coefficients. Look at the coefficients. So these are the new coefficients. And as you can see, our ridge regression is able to shrink our X4, which was, we know that it was redundant. So 0.04, it's doing a good job here, but here it's not necessarily doing a good job because it's still, it thinks that X5 should be in the model. But look at Lasso and ElasticNet. Both of them completely got rid of X4 and X5. And we know because we were simulating that data. So they're doing a great job. So for that reason, if I compare the RMSE of the test sets between these 4 models, I will pick the one that has the smallest RMSE. I call it the winning model. Okay. So for linear model, of course, it's not going to change, but for, let's see how much we can improve it for, this is our ridge regression, right? So RMSE for the ridge, a lot, right? It went from 2.03 to 0.89. So ridge regression was doing an awesome job, but I already knew that Lasso and Net should do a better job, even better job. Let's see if you can get a smaller RMSE. Yes, 8.1, sorry, 0.81. And then finally, ElasticNet. So this is my winner. So ElasticNet in our simulated data is the best model. Okay. Yep.
And didn't you say like there's no way to tell which one is going to perform better on a given data set? You just have to run.
We're going to talk about it right now, right?
Oh.
So at the beginning of the lecture, we said that we're going to work with 2 data sets. The first one is going to be simulated data, and because we know the answer, we want to see which one is better. But the second one is real world data, and see if those ridge regression, penalized regression, basically are going to be able to outfit the linear regression model or not, right? So here, and again, even in real world application, you will go with the model which has the smallest RMSE. Okay. But we'll see that this huge improvement not necessarily happens many times. Okay. It depends on the context of the question. So here, it was a perfect fit. And so that's why I use the simulated data. All right, and then the rest of it is just repetition. We don't need to do them again because these are independent of the alpha. These are for different alphas, not only alpha 0 or optimal alpha. Okay, I think we're done for this notebook. Were you able to beat the linear regression model? The answer is yes. What do you conclude? Okay, the conclusion is that here, the penalized regression, we're able to increase the bias a little bit, but the amount of reduction in variance was so high that the overall RMSE was dropped. Okay, so I put bunch of extra links for you. So for example, and I think, yeah, if you're curious to know more about the standardization feature in Python, so this is a good link. And here's an example. Okay. So that was our first example. The next one is going to be a real world example, right? We're going to work with the Boston data set. And from that data set, I just wanted to work with 2 variables. But again, you can think of, I don't know, you have 30 variables and you want to think of polynomial version of 5 of them to the power of 5. So you have 35 variables and then you can extend the model. I think your homework is a little more challenging than this one. But again, you get the idea how things should work. Okay, so what are the variables? Price from one hand, and the other one is LStat. So this LStat stands for the percentage lower status of the population. So not surprisingly, the higher this percentage, the lower the price of the average price of a house. And so let's import the libraries, look at the head of the data set. So this is our data set, and we want to see if I added the polynomial to the power of 10. So x to the power of 10 to the power of 9, and see if ElasticNet or Lasso are able to get rid of a bunch of these variables for us. Getting rid of the features itself alone is not enough, right? Because of course, if you increase the alpha, it's going to get rid of a bunch of those features. The more important thing is that if the new model performs better than the linear model in the test set, so that's your criteria, decision criteria, right? Not necessarily, again, if you want to stick to the interpretability, yes, you use Lasso and you shrink all these things maybe to 3 variables and you start interpreting them. But if your goal is to make a more accurate model, you have to go with the model with the smallest RMSE. Okay. All right, so this is what we want to model. Again, price versus LStat. And I don't know, if I want to guess, so I say that this is quadratic, maybe x1 and x to the power of 2 is enough. But for fun, we had x to the power of 10 and see which one is surviving at the end of the day, which feature is surviving if I do Lasso, if I do ElasticNet. Okay, so that's the plan. You good? We need to normalize the feature. So price is between 10 and 15. I think these are $1,000 and these are the median price for different cities in Boston. And we have 500 cities, I believe, 503 observation in the data, and LStat, and these are percentage. So again, why we need to standardize the features first? Because the coefficient of LStat, these ones, beta 1, beta 2, beta 3, or W1, W2, you wanted to make sure that you can compare that. Look at that. Actually, I'm glad that I have to the power of 10. Look at this number. LStat is 4.98. Of course, to the power of 10, this number is huge, right? So of course, the coefficient, the weights of this LStat 10 is going to be a lot higher than the coefficient of LStat itself. So for that reason, I have to standardize all these variables to make sure that they lie between -3 plus 3 with 99% probability, and then compare the coefficient or shrink the coefficient or get rid of the coefficient. So that's why, you guys remember, at the end of the day, for this class, you have, I don't know, 10 models on hand, and sometimes you're confused. Should I do standardization? Should I do not standardization? So penalized regression is the one that you must do standardization. And I will make sure that I will emphasize it enough for which model you have to do standardization, for which model you do not. But in general, it doesn't hurt. So standardization in general doesn't hurt, but you lose interpretability for some of the models. Well, you get different kind of interpretation. All right, let's go ahead and use the standard scalar. And again, the steps are completely the same. We can check if we get the first number correctly. So for example, this is not frame, this is LStat. LStat. Let's see if I can get this number, right? So is it that one, 24? Let's see, sorry. So for example, let's see if I can get the correct standardized version of 24. So I have to do 24 minus the average of price divided by standard deviation of price, right? So 24 minus the average of price, 22.53, and divided by 9.19. So this is what I do here. And if you do the math, you will get 0.15%. So this is what we got here exactly. So it's doing its job correctly. It's a good practice. I usually tend to do that because I want to make sure that everything is being done correctly behind the scene. Okay, I make my data frame. Again, the steps are exactly the same. And so this is my scaled data frame now. And if I plot price versus LSTAT, remember, so this is important, guys. The pattern does not change. Okay, this kind of a standardization does not change the pattern. The magnitude is changing. I repeat myself, it's not like log transformation. Some transformation change the pattern as well. That's the objective of the transformation. But these ones that we use in machine learning, they don't change the pattern. Just change the magnitude because sometimes you're calculating distance. What is L2? L2 norm is a distance, right? We talked about those distance. What is L1? It's a different type of distance. When you're calculating the distance, you have to make sure that all the features are standardized. Okay, we're going to go ahead and split the data and 20% test size, 80% train size. And again, they're highly correlated. And again, just in order to have some benchmarks, some idea which one of them are statistically significant, we're going to use the stats model API and then look at the summary. So our linear regression model is doing a pretty decent job, 67%. And even with 10, look at that, even with 10 features, which is highly nonlinear fit, maybe we are overkilling it, right? Maybe the bias is too small, but the variance is going to be high. But what we'll see, that's the whole reason that we're doing penalized regression is to figure out that one. But it's doing a decent job, adjusted R score 66%, 67%. Look at the coefficients. So I strictly look at the p-values. So constant, I don't care. They're not significant, not significant. It seems that none of them are significant, right? So even though the R score, adjusted R score was high, but I don't get any causality out of this linear regression model, okay? Because look at that, the p-values are all greater than 50%, which is very, very bad, over 30%. This is, so basically I don't have anything. When it comes to econometric parts, when I, for example, if I want to come up with a story for this regression model, I don't have anything because none of them are significant, okay? So I know I have to do something about it, right? So again, the steps are the same. We're going to import Ridge, again, everything, all the models and with their cross-validated versions. And now the difference between this notebook and the previous one, I'm not passing alpha is equal to 0. Okay, there's a reason for that. So let's talk about it. So here, I just wanted to, in the simulated data, because the data was designed for these kind of problems and the X was normally distributed and things like that, the algorithm was able to converge if alpha was equal to 0, right? However, for real data, I want you to, your starting point should be past nothing, just past all the default values, right? So for example, I don't know, the default value for lasso alpha is equal to 1, right? And how should you, again, you start from alpha is equal to 0, and then you calculate the coefficients, you'll see that the coefficients are different. And then you wonder what happened. Alpha was 0, but the coefficients are different, so what's going on? And then you dig deeper, and maybe it's a good idea to read the documentation. So for example, let's do documentation for ElasticNet, or let's do Lasso. We are more familiar, right? So Lasso. Let's learn document. So the first thing is the documentation for Lasso. And let's read through alpha, right? It says that, okay, the default value is 1, alpha 0 is equivalent to OLS, solved by linear regression. For numerical reasons, using alpha is equal to 0 with Lasso is not advised. So where do you think this is coming? So actually, I leave it as an exercise for you. I say that I want you to go ahead and remove the warnings and run the models and see what you get. What you will get at the end of the day is that the algorithm is complaining. It says that with the tolerance level that you set, the model is not converging. Okay, it's not converging. Why? Because it's doing gradient descent. Lasso is doing gradient descent. ElasticNet is doing gradient descent. There is no closed form solution, right? Do you remember those shapes that we talked about? Maybe there's a local minimum, or the path to the optimal coefficient is jumpy. You're going to see all those things in a real world data set, right? So for that reason, I know that when I want to if this is my starting point for Boston data set, I should not pass alpha is equal to 0. You can. Actually, this is the way that I did. When I was putting together this notebook, I started with alpha is equal to 0, and I realized that the coefficients are different. So, okay, it doesn't make sense. And then I look at the warning, it says that the algorithm is not converging. So that's the story. Okay. We are going to start with the default value. It means that for Ridge, alpha is equal to 1. For Lasso, alpha is equal to 1. For ElasticNet, alpha is equal to 1. So basically, we're starting from alpha is equal to 1. Let's fit the model and then make predictions. Exactly the same code. I just borrowed from the original notebook. And look at the coefficients. Right away, not the coefficient, the predicted values. Right away, something is weird, right? So for example, this is the true numbers. Linear model, okay, the Ridge, Lasso, and ElasticNet. Look at the Lasso. All the predicted values are the same. Okay, let's look at the coefficient and we talk about why. Let's look at the coefficient. Okay, the Lasso, if you look at all the coefficients are equal to 0. What's going on? What do you think? Because alpha, that the default alpha was 1, and it seems that for this setup, alpha is 1 is huge. It's penalizing everything. So what is this number? 0.009. If all the coefficients are 0, so what is this constant? Yeah, what is that intercept? That's the average y, right? So yeah, if you plug 0 to the coefficients and you just run regression, you basically get the average y. Okay. Yeah. All right. So this is, we know that we are getting the average, and it's literally a line. So if my regression is literally a line, which one is higher, bias or variance? Bias, right? Because on average, you're not capturing anything, right? If I go back, if I want to actually plot this, you remember what was the number, 0.0019? This is the average y, right? If I plot this average y, it's capturing nothing. So the bias is huge, but what about the variance? Tiny. Because regardless of what kind of random samples that I pick from this data set, the average is going to, well, that line, the slope is not going to change that much, right? So I hope that, again, this is another version of looking at the bias variance trade-off. So right now, I know that the Lasso regression is doing a poor job. So we have to definitely optimize the coefficients. But let's move on. I just want to tell you what's going on. And even for the ElasticNet is keeping one of them, the Elastat, and then get rid of the rest of them. Maybe this is, and it's negative, right? Not surprising, right? Basically, it's plotting a simple line with the slope of minus 0.15. Okay. All right. Okay, so here's a question for you. I just want you to do this exercise and see it for yourself. If you have time, I will do it, but probably not. But go ahead and in the first cell, remove the warning and see what the algorithm is complaining. And actually use alpha equal to 0 for all these models, right? And then look at the coefficients. You expect to see the same coefficients, but you will get different coefficients. And one more thing. Okay, here's another reason, guys, that we need to do standardization. For our linear regression model, look at the coefficients. They're insanely different, right? So the first one is 10. Then to the power of 7 version, the coefficient is in order of 7,000, right? So we have to, and we need to shrink them dramatically, right? And as you can see, ridge regression was super successful in terms of shrinking them dramatically, right? So, but still, we don't know which model is doing better. So I have to look at their performance in the test set, right? So our linear regression model, RMSE in the test set 0.54, okay? I cannot say anything yet unless I compare it with something else, right? By the way, I can say about the units, right? So what's the unit of this? The price is $1,000. What's the unit of this? What does this 0.54 mean? What is your target variable? Price of the house, right? So 50, again, 100 means that $100,000. So what does this mean? This is RMSE, 0.54. Give me a number. $0.5. So you have to multiply by 1,000, so it's $540, right? So RMSE, the unit of RMSE is exactly the same as the unit of your target variable, right? So this is $550 if you want to. So it says that, you know, in the test set, the squared error, your errors on average, you know, the root mean squared error was $540, which is not that bad if you want to think about it. If the property, I don't know if the house prices or the average is 50,000. I don't know what's the year of the data set, but this is not that bad. Okay. Okay, so the next model is ridge regression. So if you look at the RMSE, okay, it's greater, right? So our linear model is doing a better job. Well, this is yet when alpha is equal to 1, right? We haven't optimized it completely. So alpha is equal to 1, it's 5.5, and not surprisingly, this is going to do a very bad job because the bias is insanely high, right? It's a flat line. This is on my lasso regression, yet it's a flat line. And then, not surprisingly, ElasticNet is going to do a very bad job either as well. Okay, so if you look at the MSE test or RMSE test for ElasticNet, it's 0.89. So this is going to, so this is poor. So far, ridge regression is doing a decent job, but still cannot outbid the linear regression model, right? So let's quickly plot. There are some observations here that I want you to pay attention. Let's plot the coefficient path for ridge regression, ElasticNet, and Lasso. So this is the coefficient path for ridge regression, right? Here I have a question for you. I think we don't have this. You don't need that one. So which of the features are the most important ones for alpha is equal to 100? So what's your answer? Alpha is equal to 100 or here. So which one is the most important one? Just name one. That's the LStat, right? So this 100 is here. So it seems that if you penalize the regression with higher alpha, so still, if any, this LStat is surviving, which makes sense, right? So maybe this is your main variable, and then you can look at the coefficients for the ridge regression, which was minus 1.99. So I can imagine that this is not necessarily a bad thing. So if I only want to keep that one in the model, look at that. This slope is around -2, which is pretty, yeah, it seems fine to me. Okay, should be less than that, but anyways. Okay, so that's the path of coefficients for ridge regression. So the ones that I want you to pay attention are for Lasso and ElasticNet, because with real world data, it's not as clean as synthesized data. So this is for synthesized data. You see, it's very clean and beautiful. When it gets 0, it's stick there, so it's global, optimal, and etc. Right? But look at the real world data. And specifically, I want you to focus on LSTAT4. So this is a coefficient, let's call it W4, coefficient for x to the power of 4. At some point, when alpha is increasing, let's say 10 to the power -3, it's big, and it's okay, it's penalizing, it's shrinking the coefficient. At some point it gets 0, right? You think that it's out of the model, but it come back again, right? And then it's forced to 0 and maybe come back again. Well, I think it's 0 from here to here and then come back again. And here's a challenging question for you. Looking at the coefficient of LSTAT4, it seems that at some point it gets to 0, but it comes back. And what's going on here? And I gave you a hint. Remove the warning message at the beginning of the notebook and see what you get when you run these things. But basically, all these things have something to do that the path for ElasticNet and Lasso is not stable. We talked about it in our matrix that we compared the 3 models, right? Why it's not as stable? Because we're doing gradient descent. Because we jump from one optimal to another optimal. Well, we can. If I do only gradient descent, it will stick to one of those local optimal. But if I do, for example, some momentum to that, it's push it from that local optimal, make it to another optimal. So that's why it's jumping. It's going up and down. Okay. But eventually, look at that. Eventually, if I ask you which one survives at the end of the day for large enough alpha, the answer is LSTAT, right? Okay, and then finally, let's do the same process for for ElasticNet. And again, it's very the same as, at least visually. Magnitude is different, but visually, the pattern-wise is the same as Lasso. And so this LStat is the one which is surviving for higher alphas. And again, LStat 4 is not stable. Look at that. Even the green one is what? LStat 3 to the power of 3. It is increasing at some point and then decreasing, which doesn't make sense, right? When you penalize something, it should shrink the coefficients, but this is what it is. It's all because of that existence of the closed form solution. All right. So by looking at the lasso, I think we talked about, yeah. So this, your homework is going to be something like this. I want you to plot these things and I ask you questions like this. So hopefully it makes solidify your saying. Let's figure out the optimal values for alphas. So for ridge regression, again, you can, I think for your homework, I'm going to do you a little more. So I want you to, because by default, it's only looking at 3 numbers, right? It's only looking at 0.1, 1, and 10. I want you to look at the range, larger range, maybe 20 numbers, okay? So out of these 3, the optimal was 0.1, so I'm gonna save it. So let's save it. And then for lasso, the optimal is 0.007. Again, not surprisingly, it's suggesting me that my linear regression was doing a decent job because lasso is trying to penalize lots of the coefficients. This alpha is very small. Sorry. No, I take it back. It's yeah, not penalizing very much. And then for ElasticNet, again, I'm not going to do the ALBA method. That was just for illustration purposes. So ElasticNet, this is going to be the alpha. I save it. Now go back and use the optimal version of the alphas and see how much we can improve the RMSE in the test set. Okay, so let's go back. Here, I'm going to put alpha is equal to alpha ridge. I think I call it optimal, yes. Yeah, well, lasso optimal, and then we do ElasticNet. Okay. So let's run this, and we keep our fingers crossed and hope that we can get a better RMSE. Well, in terms of coefficients, let's look at that. So lasso is getting rid of x5, x6. That's pretty much it. Remember that lambda was not that big, so that's why it's not penalizing that, or street tree. And the ElasticNet is getting rid of 3 of them, x6, x7, x8. And let's see, let's compare them. So our linear model, the answer is 50.54. Okay, so let's see. The ridge regression, 0.555. No, it cannot outbid. The lasso, 0.558. And then the ElasticNet, 0.557. So what's the takeaway? Okay, but when it comes to so the takeaway is that none of these penalized regression were able to outbid our simple linear regression model. But the problem with this one is that this is not a model that we have. Okay, so that's for this model. We have to use some maybe non-parametric models, right? So maybe you want to put some. You want to make sure that your f of x is more flexible, can explore the data better, maybe. So maybe we can use some other methods. Maybe, not maybe, we're going to see that the random forest is going to do a better job for this one. Okay. Because again, if I don't have interpretability and if I don't have a good prediction, so why should I use this model? Okay. All right, so I think that's all. And I don't have anything else unless there's questions. So let me see. Yeah, whiteboard. Yeah, that's pretty much it. I just wanted to, because we were not recording, I just wanted to emphasize it one more time. And that, so this is, Ryan, this is back to your point last class that you said, how come there is we can force coefficients to go to 0 for lasso and ElasticNet, but not for ridge regression, because this is how the L1 plus L2 norm will look like. And as you can see, we can get to these corner solutions. So for that reason, it can force it to 0. Okay.
So that, I mean, that kind of makes sense, but why can't you get to 0 with like the circles, like, I'm guessing it's like the corner solution, but it seems to me that you can still get to zero with the,
This one?
yeah.
Well, you have to, so this is the optimal. So whenever this contours are tangent, you know what are these contours? This is the optimization from RSS, residual sum of score, or MSE, okay? And so in 2D, they look like this. So whenever there's the intercept between the two, that's the optimal solution. It's like consumer behavior optimization in econ, when you have a budget line and you have utilities. So that tangent point is the optimal solution, right? So, and as you can see, there is no way that you can get to this point or this point. So that's the reason.
Based off of the
Yeah, if you want to get to this point or this point, you go to a higher contour, which is you're minimizing these things, so which is a bad thing. Yeah. Again, this is exactly like consumer maximization when you're looking at utility. If you're interested, this is called convex optimization. You're optimizing a concave function. So this is your concave function over a convex set. So convex set basically means that these are the closed convex sets, and then you're optimizing this function over this is called convex optimization. And the solution, I think, visually at least makes sense. Just forget about the mathematics behind it, but visually, I hope that it makes sense. Okay.
Yeah, that helps.
Okay. All right. So yeah, if there is no any other question, let me stop sharing and pause, stop the recording. Guys from home, do you have any questions? Okay, so let's call it a day. See you on Thursday.